the last one that we have is the spin quantum number. This is ms. It's an ms. ms can have values of +1/2 or -1/2. This specifies the orientation of the spin axis. So we say, and this isn't exactly correct, but we say that an electron is either spinning in one direction, so we call that spin up, or it is spinning in the other direction. We call that spin down. So we would call this +1/2, -1/2. As far as the up-down definition, I'm pretty sure that's just an arbitrary assignment. But it has to do with one of them is kind of spinning in one direction, one of them is kind of spinning. So one of them is kind of going clockwise, one of them is going counterclockwise. This is generally called spin up and spin down. But up and down is also not really with respect to anything, so it's just kind of something that we say. No more than 2 electrons can occupy the same orbital. The 2 electrons that are in the same orbital, they have to have opposite spins. We can kind of relate each of these quantum numbers to the solar system model. So you can relate, let's look at Earth. This is totally not how this works, but let's give the quantum numbers of Earth. So Earth's order from the sun, that would be like its energy level. It's represented by N. So N is like what order it is from the sun. Revolution around the sun, that would be like the orbital. That would be the L and the ML. So it would be the angular momentum and the magnetic quantum number. So that would be the shape of its orbit and where it is in that shape. The Earth's rotation about its axis, that would be like its spin. So if it's spinning gotta get Australia in there. If it is spinning in one direction, we would say that that is +1/2. If it is spinning in the other direction, we say that in one direction, we say that it's +1/2. If it is spinning in the other direction, we say that it is -1/2. However, an electron can't exactly think about spin with an electron because it's just a point. There's really no rotation that it can actually undergo. Instead, we say that the spin is related to its magnetic field. An electron is kind of like a magnet. So, oversimplifying this, we say that it has north and south. Well, it does have north and south. In one case, we say that it's oriented like this with respect to the atom, and in the other case, we say that it's oriented like this. And we demonstrate that like that. So in this like arbitrary way of ordering things, we would say that this is plus 1/2 and this is minus 1/2. Something that's spin up, we say that it is plus 1/2, down is minus 1/2. Again, up and down is kind of arbitrary because there's really no up and down in like space, but it's easier to talk about. 2 electrons in the same orbital must have an opposite spin. These are said to be paired electrons. So if you have, so we do this by kind of representing it like that. So if you have an up and you have a down, then these magnetic fields actually will cancel each other out. That's the theory. If the electrons are paired, then we call the material diamagnetic. It's not attracted to magnets. Atoms that have more electrons that spin in one direction than another are unpaired. These unpaired electrons cause materials to be paramagnetic. Those would be attracted to magnets, at least weakly. When we talk about spin particles, we have 2 names for them. First one is called a fermion. Fermions are particles that have a half-integer spin. Included in this are electrons, protons, and neutrons. Then we have something called a boson. A boson is a particle that has an integer spin. So where these have ms equals plus or minus 1/2, this would have a spin of 1 or 2. Well, these could also have 3/2, but they have half-integer spins. That's part of what we think separates things that like are massive from things that aren't. It's at least my understanding of it. The last thing that we move to is something called the Pauli exclusion principle. Pauli exclusion principle is where these definitions become applicable. This states that no 2 fermions in the same atom can have identical values for all 4 quantum states, all 4 quantum numbers. So no 2 electrons can have the same 4 values. Bosons, they can do whatever they want. They don't have, they can occupy the same states. It doesn't apply to bosons, only fermions. So like protons, electrons, and neutrons. Oh, this is where the energy levels kind of come in. If you remember from like high school chemistry, you had something that was like you had the 1s, then you had the 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. And then you would know the number of electrons that something could have. And you would go like that, and you would count them. So 2, that would also have 2. I think P could have, and then you would just go like that, and then you would give the 2s squared 2p to the 6 or whatever, you would count it out like that. That's where these energy levels actually come from. So, yeah, the first energy level, the 1s, that's filling up the circle. When you're filling up the p, that's the dumbbells. The d is the clovers. And F, I'm not even going to try to draw. But that's where all this comes from. And chemistry is the study of all of these outer electrons. But they also perfectly describe the periodic table. That is where I am going to end chapter 29. This has definitely been an experience. All right, have fun.